Good morning, everybody. Thanks for coming to this session. I believe in the meantime our speaker is preparing himself. Just let me give you a short introduction. The session will be chaired with Dr. Selpi from Chalmers University and myself. My name is Ljubo Vlačić. And we will try to stick to the schedule, so don't be upset. We are going to give you always warning about 2 minutes before the end. And as you know, each presentation will be included in poster sessions, so therefore there will be plenty of time for discussion. If you are ready, are you? So please take the floor.
Okay.
So the speaker for today, first one is Alexander Rahman, and other author is David Filia and Javier Guzman. They will be talking about Bayesian framework for preventive assistance at road intersection.
Okay, thank you for the introduction. Good morning, everyone. So I'm going to speak about this paper, Bayesian framework for preventive assistance at road intersections. So I will start this talk by speaking a little bit about ADAS. So as you know, there are more and more of ADAS in modern vehicles. We can classify this ADAS in 3 types. The first type is comfort ADAS, so it aims to help the driver to perform difficult or boring tasks such as the parking. There is also safety ADAS, which aim to avoid accidents, and one of the best examples is the automatic emergency braking, the AEB. And finally, as you know, there is more and more autonomous driving, which aim to help the driver to do something else than driving. In this work, we focused on safety ADAS. So I will come to the problem by explaining how conventional safety ADAS work. They actually perform risk assessment by classifying the situation on scale from safe to critical. And when it infers that the situation is dangerous enough, it starts to provide assistance to the driver. So currently it can be in the form of warnings, so there is an alert that says to the driver that there is something wrong and that he has to react right now. And we can also actuate automatically on the vehicle with the AEB to avoid the collision. So actually that works that good, that can save lives. However, such assistance can be called curative assistance as they are provided at the last moment. This is the last resort, actually. Actually, most of the conventional ADAS do not consider the fact that every driver is different. But we know that every driver is different. 2 drivers will not behave in the same manner for the same situation. And the drivers will not understand the situation in the same manner as the safety ADAS. For example, one aggressive driver will consider the situation is safe, while it will be inferred as dangerous by the safety ADAS. And on the contrary, for a relaxed driver, he will maybe consider the situation is already dangerous, while it will be inferred as safe by the safety ADAS. So actually, if we want to suit most of the drivers, we have to push the decision threshold to the left, to the right, to dangerous and critical situation. So that will help to avoid false alarms for aggressive drivers. However, we will lose a lot of time for a relaxed driver. And in this work, we work towards what we call preventive assistance. So basically, it's assistance that will behave as a co-pilot. A co-pilot knows how the driver usually behaves in a given situation, and he will do his best not to wait for the last moment to provide assistance. He will do his best to provide assistance in the form of recommendation or advice to let the driver have time to understand and to react comfortably. So this is what we're working towards. So this is the content of this presentation. I will speak about the proposed Bayesian framework, then I will show some experimental evaluation, and then I will conclude. So let's start. So this is the case study that we choose. This is a simple one, the approach of a single vehicle to stop intersection. And actually we have some constraints. The first one is the problem that we have. We want to get a co-pilot-inspired ADAS. So we have to consider differences between drivers, and we have to be able to trigger preventive assistance, but also curative assistance. And the second constraint is the industrial context of this work. We have to to do our best with the sensors that are already in the vehicle, and most of them are cheap, but they are very noisy, and we also have to use road level and imprecise digital map. And actually the baseline of this work is based on this Bayesian network. It was developed by Stéphanie Lefebvre a few years ago, and this is with the approach comparing intention and expectation. So basically we can perform risk assessment by computing the probability, so at road intersection, that the driver has the intention to go while he is expected to stop. So that works well. However, there are some limitations with respect to our problem. The first one is that it does not make the difference between the different types of assistance, so it does not know the difference between a warning, between a AEB and an advice, so preventive assistance, and so far it only observes the vehicle state. It does not look inside the vehicle. So this is actually why we propose to extend this Bayesian network. So this is the original one. We have actually 4 layers, one for the observations, we observe the vehicle speed and the vehicle position. And with that we can infer the intention of the driver. Does he have the intention to go or to stop? And we can also infer what is expected. Do we expect the driver to go or to stop? So this is with respect to the context. And the first extension is about the assistance. We add a 5th layer to model the assistance and to model the 3 types of assistance that we want to, the model to take into account. So we can model whether or not it's pertinent to provide at time t automatic actuation or a warning or an advice. There is a second extension. So here the rationale is that there is a significant time between the moment at which a driver starts to actuate on the vehicle and the moment at which we can start to observe change on the vehicle state. This is why we propose to include observation of the driver actuation within the Bayesian network. So we add some observations, the state of the brake pedal and state of the gas pedal. And with that we can infer whether or not the driver has the intention to react to the situation. So basically this is the final Bayesian network, the extended one. We have got 15 variables, which means that we have to define 15 conditional probabilities. I don't have time to present all of them, so I will focus on the 2 that are, according to me, the most interesting and the most important. So the first one will be about the real vehicle speed. Real vehicle speed here, and the second one will be for assistance, and that will cover the 3 types of assistance. So I start with the vehicle speed. The real vehicle speed actually highly depends on the intention of the driver. If the driver has the intention to go, then we can consider that the speed of the vehicle will be more or less constant. This is what we see on the left. However, if the driver has the intention to stop, then we will get such a speed profile. The vehicle will decelerate to the intersection. But actually we know that every driver is different, so 2 drivers will not decelerate in the same manner. This is why we propose to include such features in the Bayesian network. So we propose to learn how drivers usually decelerate when they approach to an intersection. And for this purpose we used Gaussian processes, so we took some training data. You can see them with the blue dots here. And we used the Gaussian processes to model the average profile with uncertainties. So it's shown here in red. So this is for the real vehicle speed. I come now to the assistance. We have, again, 3 types of assistance that we want to model. The automatic actuation, the warning, so both of them are for curative assistance. And we want also to model advice, so for preventive assistance. And for each type of assistance, we have to consider several things. The first is that we have to consider the intention of the driver, but also what we expect the driver to do, given the situation. We have to take into consideration the reaction time of the driver, but also the time response of the machine. And we have to consider also a minimum and a maximum acceleration that will be tolerated by the driver when he starts to decelerate after being provided with assistance. So basically here, I want to show that we cannot provide automatic actuation too early, otherwise it will result in too smooth braking acceleration, and then the driver will not consider the assistance as very pertinent. And on the contrary, for preventive assistance, we cannot provide an advice too late, otherwise the driver will not have time to understand and to react comfortably to the situation, and he would have preferred to have a warning or maybe an AEB. So this is for the types of assistance. Okay, so I presented very briefly the Bayesian network. I come now to the experimental evaluation. So again, we are in the industrial context where we had to take the data that was already in the vehicle. So we used the vehicle canvas to get the vehicle speed, the state of the pedals. We had localization with the standard GNSS, and we used OpenStreetMap maps and a dedicated navigation system to get the electronic horizon. We created a data set. It was done on crossroad with 4 different drivers, and at the end we had more than 260 samples, including safe and risky situations. So I come now to the qualitative results. So basically how the Bayesian network behaves when it's provided with inputs. So you see on the left the observations. You see so the vehicle speed here in blue. This is what we recorded here. In red we have the velocity profile that we learned for the driver using Gaussian processes. On the bottom we see that we see the state of the pedals. So in blue, the state of the gas pedal, and we see that the driver actuates on the gas pedal and then starts to release it. Sorry. And in red, we see the state of the brake pedal, and we see that the driver starts to brake. On the right, we see the inferences of the Bayesian network. So in green, we have the probability that it would be pertinent to provide, it would be pertinent to trigger an advice to the driver. In blue, the probability that it would be pertinent to trigger a warning to the driver, and in red, the probability that it would be pertinent to trigger automatic actuation. And we see that these 3 probabilities are very low all over the run, so there is no inference of pertinent assistance. For a risky situation, so the driver does not have the intention to stop, we have the same observations here, but we see here that the vehicle speed is more or less constant, the driver does not decelerate, and we see in the bottom that the driver does not release the gas pedal and does not actuate on the brake pedal. And we can see on the right the inferences. We have the 3 probabilities. And in green we can see that the probability that it would be pertinent to trigger an advice starts to increase about 30 meters before the intersection. If the driver does not react, then the probability that it would be pertinent to trigger a warning starts to increase about 25 meters before the intersection. And again, if the driver still does not do anything, then the probability that it will be pertinent to trigger AEB starts to increase about 10 meters before intersection. So we see here that the Bayesian network allows to infer, we can see that each type of assistance can be inferred as pertinent at different times. And we see also that it's inferred as pertinent on very short periods. So the Bayesian network here allows to select the right moment to trigger assistance and can select the assistance that is the most pertinent given the time and the state of the vehicle. Okay, so I come now to the qualitative results. So we have the rates of true positive, false positive. So we made it for either curative and preventive assistance, automatic actuation, warning, advice, and I want here to show the differences that we can have between the proposed model, the model that we propose, and the original one that does not consider differences between drivers and that does not observe the actuation of the driver. And what we can see here is that, okay, for automatic actuation, with our model, the extended one, we get 100% of true positive, 0% of false positive. So it's a bit better than with the original model, but the most interesting is for warning and advice. We start with about 0% of true positive for warning and advice with the original model. And with the extended model, we come to more than 80% of true positive with very few false positive. So what I want to show here is that the performance of the original Bayesian network here can be improved by considering the differences between drivers and by observing the driver's actuation that allows to infer whether or not the driver has started to react to the situation. Okay, I come now to the conclusion. So we proposed a risk assessment framework, which is based on the comparing intention expectation approach using the Bayesian network. It was proposed by Stéphanie Lefebvre. It's compatible with car manufacturer constraints, so we use very poor sensors. It allows to consider that each driver is different, so we use prior knowledge about the driver. It's able to trigger curative assistance, but also preventive assistance. This is what we were looking for. As a conclusion, we can say that if we want to trigger preventive assistance, the risk assessment should include prior knowledge about the driver and should observe the driver actuations. In terms of perspectives, we work with a basic case study, so it would be very interesting to extend it to other situations, so other intersections with other road participants and also with roundabouts. You should also develop an HMI that will provide information to the driver when it's provided with advice. So I think it's a very difficult task. And also, so far, the model does not allow to consider the faults that we can have in digital maps. So it would be very interesting to work on this.
Thank you very much. 1 minute is left for a question. Is there any question, please?
So I noticed that you had different probabilities for different types of warnings, essentially.
Yeah.
But I noticed you mentioned about 30 meters and then 25 meters between the preventative and having some sort of warning, and then the next one was at 10 meters. So these are all quite close together. And if you're traveling at 30 kilometers an hour, is there really any time for a driver to actually make any sort of effect?
Yeah, actually, it considers the reaction time of the driver and also the acceleration that is allowed when the driver starts to react. So we took a quite high reaction time, 1.5 seconds plus 0.545, I don't remember, second for the reaction time of the machine. So I think we can, discover this, and at the end, so I do not show this in the presentation, but we have for curative assistance, after being assisted, the driver undergoes about an acceleration of about -5 meters per second square. And for advice, so preventive assistance, we have an average acceleration of about 2.4 meters per second square.
Thank you. Could you please join me in thanking the speaker?
To the second speaker in this session. The speaker is John Michael Scanlon from Virginia Tech, and he's going to present preliminary potential crash prevention estimates for an intersection advanced driver assistance system in straight crossing path crashes.
Hello. Oh yeah, thank you. Thank you for the introduction. My name is John Scanlon. I'm a researcher at Virginia Tech, and today I'll be presenting some work that we've been doing evaluating the effectiveness of an intersection driver assistance system in the U.S. vehicle fleet. Before I begin, I'd like to acknowledge the sponsors of this work. I mean, not the sponsor, the co-authors of this paper, Rini Shironi and Dr. Clay Gabler. So intersection crashes are among the most frequent and lethal crash modes in the U.S. Each year they account for about 1/5 of all crashes and 1/6 of all fatal crashes. That's over 4,500 fatal intersection crashes each year in the U.S. So I wanted to start off this talk by giving an example of a fatal intersection crash that occurred in the U.S. So in the scene diagram that I show in the middle, this black vehicle was being driven by an 84-year-old male. He slows down for a stop sign, he looks for oncoming traffic, and he never comes to a complete stop. And then when he feels it's safe, he accelerates into the intersection. And what this driver failed to detect is this blue vehicle, or this vehicle indicated by the blue arrows. This being driven by a 70-year-old female. She says she saw the male slow down for the stop sign, but when he fails to stop, she doesn't have enough time to react, and she ends up striking him in his driver's side door, and fatally injuring him and his right front passenger. So when we look at these types of crashes, well, one way to potentially prevent them is through the use of an intersection advanced driver assistance system, or as I'll call it, IADAS. And the way IADAS works is if a driver is to enter an intersection when it's unsafe, the driver can either receive a warning if the system feels that an imminent crash is about to happen, or the system will automatically brake, so using like automatic emergency braking, or AEB. The idea being, by slowing down the vehicle, you have the potential to either prevent the crash altogether or possibly mitigate injury consequences associated with it. There are several different types of common intersection crash modes that are seen in the U.S. The most common is the straight crossing path scenario, where there's two non-turning vehicles that intersect within the intersection. The second most common type of crash is the left turn across path, with a vehicle traveling from the opposite direction. The third most common is the left turn across path, with a vehicle traveling from the lateral direction. Then there's turn into path crashes, so that's right turn into path or left turn into path. And then there's other miscellaneous intersection crash modes. So that can be things like a driver departing his lane and striking a vehicle coming from the oncoming direction. So for this study, I focus on the most common type of intersection crash mode, the straight crossing path scenario, that accounts for half of all fatal intersection crashes in the US and about a third of all intersection crashes. And because of that, these crashes are the highest priority in terms of intersection crashes in the US. So the research objective of this project was to estimate the number of straight crossing path intersection crashes that could be prevented if every vehicle in the US was equipped with one of these IADAS systems. So for the methods, there's four main steps to the study's method. The first step is to extract a set of real-world straight crossing path intersection crashes taken from the US driver population. The second step was to then reconstruct these crashes, and that includes reconstructing the position of the vehicles as they approach and enter the intersection, and then to also reconstruct their most likely kinematics, so how fast is the driver moving. The next step was to then take all these reconstructed crashes and then resimulate them as if the vehicles had been equipped with some sort of IADAS system, so that includes sensors and some sort of warning algorithm. And then lastly, we accumulated all these, the results from all these different studies, all these different crashes, and from that we can generate benefits estimates, or the number of crashes that could have been prevented. So the data source that we used for this study was the National Motor Vehicle Crash Causation Survey, or NMVCS. This was a special study done by NHTSA from 2005 to 2007, over a 2.5-year period. And it's a special study because the crash investigator had to have been there before the vehicles were cleared. And because of that, they're able to perform interviews on scene and actually start to gain an understanding of what exactly happened prior to the crash. Like, did one of the vehicles stop prior to accelerating the intersection? Did one of the guys blow through a stop sign and didn't see it? That sort of information. And then all in all, we had 459 straight crossing path crashes included in our data set. So in terms of performing crash reconstructions, we divided the pre-crash and crash into 4 distinct phases. And we started our reconstruction process from impact. So we actually performed impact speed reconstructions using PC crash simulation software. And the way the software works is you will feed it rest positions, and you'll feed it their impact positions. And using software, you can begin to optimize and figure out what the vehicle's most likely speeds were at impact. Then using these impact speeds, we're able to estimate how likely the driver was to have taken some evasive action. And actually in intersection crashes, evasive action is very common. It happens at about 4/5 of all intersection crashes in the US. The next step was to then take all, given whether the driver took evasive action or not, we'd model the intersection traversal phase. An intersection traversal phase can be after a driver slowed down for a stop sign, he might accelerate, or maybe the driver had a green light the whole time and he's just traveling through. And then the intersection approach phase is the driver's either deceleration as he approaches the intersection, or maybe just traveling through speeds. So in the end, we would take all 459 crashes, both vehicles in these crashes, and we reconstruct their path, and we have this accumulation of these crashes now. And now we can use these crashes to begin to simulate the potential effect in this IADAS by placing hypothetical IADAS systems on these vehicles. So on the right here, you see that we begun to place sensors on them, and geometrically we can say, okay, at this time point, the vehicle would have fallen within these sensors. We make some assumptions regarding when the system could have detected an oncoming vehicle, such as when the driver would have first entered the intersection, there would have been no sightline obstructions. That's one of the assumptions we made in the study. And then given that the oncoming vehicle was in this sensor beam, we set time to collision thresholds, which are shown on the right, in order to decide when IADAS was going to deliver a warning to the driver. So for this study, we just focused on an IADAS that would warn the driver, and we'll see if that would be effective or not. We considered 3 separate time to collision warning thresholds. The first threshold was a 2-second warning threshold, then a 2.5-second warning threshold, and then a 3-second threshold. And we made the assumption that after the driver would have received this warning, it would have taken him 1.3 seconds to have reacted to this warning, which is it's an average value taken from a previous simulator study looking at how long it takes a driver to react to a cross-traffic intersection scenario, given that he had received a warning, or they had received a warning. And then we assumed the driver would have reacted by performing evasive braking. And we used a 0.58 G braking deceleration, which is typically observed by drivers in straight crossing path intersection crash scenarios. Okay, so for the results, on the y-axis here you have the 3 different time to collision thresholds that were being evaluated. On the x-axis you have the percentage of crashes. And now starting all the way from the right in these grayed out bars, you have the how many crashes our model predicts could have been potentially avoided. And our model predicts that 19 to 35% of these straight crossing path intersection crashes could have been potentially avoided, or could have helped the driver to potentially avoid these crashes given that he had received a warning. For crashes that couldn't have been avoided, but the driver still was able to respond earlier, you'd have modified impact conditions, which are the middle bars. And we found that 19 to 34% of these drivers would have had modified impact conditions. And what this implies is that the driver would have different impact, or the vehicles would have different impact speeds, different impact configuration, and when that happens, you'd expect different injury consequences. So there's the potential for injury mitigation benefits. That wasn't considered in the study, just was interesting to note. And then lastly, our model predicts that 46 to 47% of these crashes would have been unchanged. And what that essentially implies is that the warning wouldn't have been received early enough for that the driver to have been able to respond and potentially have avoided these crashes. We also looked at the effect of the pre-crash movement of the drivers on the potential effectiveness of these systems. In general, these straight crossing path crashes can be divided into 2 different categories. There's the crashes where at least one of the vehicles stopped, or they're rolling stop, prior to accelerating the intersection. And then there's the crashes where neither vehicle stopped. And they both roughly represent about half of the straight crossing path intersection crash population. So for the situation where at least one of the vehicles had stopped, we find that the effectiveness of these systems were between 24 to 49%. And then for the situation where neither vehicle stopped, we found that 13 to 17% of these crashes could have potentially been avoided. And so that's 2 to 3 times more effective when at least one of the vehicles stopped, which is to be expected because the driver has now more time to respond and avoid the potential crash. So there's some limitations that I should point out with this study that are important to consider. First, there's considerable variability in how drivers behave in intersection crash scenarios and also just in general. There's different acceleration rates for drivers, there's different traversal speeds. Some drivers are more likely to have taken evasive action. And our approach was to take an average kinematics perspective, so to consider the average driver, and that would be their most likely vehicle behavior. Second, we made several best-case scenario assumptions. Specifically, we made the assumption that when the first driver had entered the intersection, there wouldn't have been any sightline obstruction between the vehicles, which may not necessarily be true, because there's other vehicles on the roadways, there can be obstructions in the median. That was just an assumption we made in the study. Third, we took a very generic approach to modeling when IADAS would decide to deliver a warning to the driver. These systems are obviously highly proprietary, and our approach was to take typical time to collision warning thresholds that we know these systems are roughly around and consider several different time to collision thresholds. Fourth, we didn't consider that the driver may take evasive steering action if he had received a warning, which could lead to greater benefits. And also, we didn't consider automated emergency braking in the system, AEB, either. And AEB would have the ability to respond faster than a driver would respond, so we'd expect additional benefits from a system like that. And then lastly, we didn't consider other roadway traffic. So maybe I avoided the first crash, but then I was impacted by a second vehicle. So that could have also happened. So in conclusion, our results indicate that IATIS has the potential to potentially prevent 19 to 35% of U.S. straight crossing path intersection crashes. Our model also predicts that IATIS is expected to be 2 to 3 times more effective when at least one of the vehicles stops prior to accelerating the intersection. And then lastly, injury mitigation is still possible for these crashes with modified impact conditions. We're doing an analysis on that now. Hope to have our results soon, but that's just also something to note. And with that, I'd like to acknowledge the sponsors of this work, the Toyota Motor Corporation and the Toyota Collaborative Safety Research Center, just for funding this research, and I will take any questions.
Yes, questions, please?
So in your calculations, did you assume that both vehicles in the intersection had the ADAS system, or only one?
Yeah, and in this study, we did assume that both would have the IATIS. Yeah.
Thank you.
Other questions?
So automaker try to give responsibility for any accident to the driver instead of they try to take liability. So when you introduce this kind of ADAS system, what's the stance of insurance company? For example, there's a collision. The second collision is more, the detrimental. The damage of a second collision is very high, rather than the first collision in a highway traffic. So if we introduce an ADAS system that could avoid the second collision, then we reduce the fatality in accidents. So this kind of ADAS system is very helpful, but what I'd like to know that the insurance company's stance when introduce this ADAS system, and whether the automaker will take a liability on that, or the insurance company will cover the outcome of the accidents.
That's actually kind of an interesting point. So in these actual intersection crashes in the U.S., specifically the straight crossing path, most of the damage is actually incurred by the first event, so that first impact. It's, I think, 97% of these crashes, the most damage is incurred by the first event, but there's also the potential for secondary impacts with other vehicles, and also off-road objects. So, and I'm not going to speak to the insurance side of things, but yeah, thank you.
Any other? Oh, please.
You mentioned that you use PC crash to reconstruct the accident. How do you satisfy with the accident reconstruction? Do you think it's good enough, or there's some improvements to do?
So we use PC crash, the software. I think there's a lot of strength in the software. It accounts for things like CG location, mass of the vehicles, vehicle stiffness, and in general, but we've never personally validated it in a real-world setting, but I know the models have been validated in several past studies. So yeah, and it seems reliable. If we change certain elements of the optimization that the software does, the results seem to be repeatable, especially among different researchers doing it. So yeah, I like it.
Thank you, John. I think we close the presentation now, and thanks to John again.
Okay, we have now the third presenter. It's about probabilistic situation assessment framework for multiple interacting traffic participants in generic traffic scenes. The speaker, my understanding, is Walker.
Right.
Okay. Yeah. Please take the floor.
Okay. Good morning and welcome everybody. Today I would like to present some piece of work which is part of a joint project between the Honda Research Institute Europe and the Technical University of Darmstadt. So the initiator and leader of the project is Julian Eggert from Honda Research, and there are two PhDs doing most of the work, like Stefan Klingelschmidt and Florian Damaro. The main contributor of the paper is Stefan Klingelschmidt. Unfortunately, he can't give the talk today, so I'll do it instead. My name is Volker Willert, also from TU Darmstadt, heading the Mobile Robotics and Autonomous Systems group. So, what is the question we would like to answer with this piece of work? Assume you have a traffic scenario, yeah, and within the traffic scenario there is more than one traffic participant. And now the question is, how important are the interactions between these traffic participants to assess the situation, right? So, and in order to do so, we want to model this in a probabilistic framework. And in the following, I'd like to convince you that these interactions are important for several reasons, and that also a probabilistic modeling, especially for this type of problem, is suitable. So let's start with a simple example. Here we picked out an entering scenario. So here you have a car entering on a driveway, or driving on a driveway, and it wants to enter this highway here, and here you see the rightmost lane of the highway. So, and this traffic participant, for example, can now execute different kinds of maneuvers. Like, for example, it can stay on the driveway, or it could enter in front of that car or behind. Of course, all the other traffic participants can do different kinds of maneuvers, for example, decelerating or accelerating. And you as a driver now have some intention, for example, if you are this driver, and now you make a guess about what the other driver's intention is, and based on this, you will do some decision what to do next. Yeah? And this is what we also want to do with a machine. So the task is here, traffic scene, future evolution, like prediction, so it's a prediction task. And for a machine, yeah, usually it doesn't know the intention of its own driver. So it also has to, in addition, infer what is the intention, what will my own driver do next. So for a machine, the inference process is a little harder than for the human being from this point of perspective. The second thing we assume is that interactions are somehow important. So we assume that these drivers are aware of the others' maneuvers, shown in here. And to be a little bit more formal, what do we now define? We have some certain finite set of maneuvers. For example, for this participant, the different participants are shown with a lower index, 1, 2, 3. Then you have certain maneuvers, for example, in front, between, or no change. This is indicated by an upper index. And then we would like to estimate the joint probability. So the probability for participant 1 is doing some action, the other one doing some other action, and so on, given some measurement here, x. So in principle, we have here an inference task for inferring a joint. And this is the gist of the matter. We would like to efficiently estimate this kind of probability distribution. And here you also see why a probabilistic modeling is suitable, because usually if you have if you have a complex traffic scene, there are usually several hypotheses or configurations of maneuvers that could take place. So it's not clear which will really happen because you have a prediction task. And if you want to explicitly keep all these ambiguities which are in this prediction, then probability distribution is like a natural way to go. Okay, there are several works beforehand, for sure, and most of the approaches do it with a probabilistic modeling. Most of the papers ignore all the other participants and are interested in only predicting one maneuver or maneuvers for one traffic participant. There are, like you've seen beforehand, several others who already try to simultaneously predict several maneuvers. But the important point here is that for getting all these different maneuvers, they assume complete independency for these different drivers. Yeah? So afterwards, once they have the tracks or the maneuvers, then they make some inference about, okay, for example, if you were to decide whether there will be a collision, how will they interact, and then they take the interaction into account. But for getting these maneuvers, they neglect it. And this is somehow a little bit like, yeah, counterintuitive. Yeah? Because if you think they are aware, then it should be relevant somehow. And this is exactly what we like to do, or what we try to do here. So we assume fully connectivity, and this means that such kind of a joint here splits into several conditional probabilities. This is according to the chain rule of probability. This is, everybody knows, this is just a generalization of the base rule. Think everybody knows from school. And if you have several participants, usually you don't have only one possibility to decompose this joint. There are several ones. Actually, you have n factorial possible decompositions. N is the number of the traffic participants you take into account. And if you would like to do exact inference, to take all these interactions into account, you also have to take into account all these decompositions. And for this problem, we tried to find some algorithm. So we had a closer look at these decompositions, and as you can see here, this is some example of one decomposition. It consists of several different kinds of probability distributions. You always have some so-called complete conditional probability. These are probabilities, a probability for participant 1 given all the other participants. This is complete. And then you have other conditionals, but these don't depend on all the other participants. So you could call them incomplete or marginal probabilities. And the thing is that learning these probabilities is easier than learning that one, because as input here, you take all the hypotheses of all traffic participants into account, yeah, like as data. But here, you don't do, but you know, like from marginalization, what you can see here, that also you don't input these different maneuvers in learning. These probabilities are dependent on the complete joint. So, and this you don't have so far because you would like to estimate, so this is a problem. Therefore, we would like to get rid of this, so we reformulated this problem, and I show you the core idea on the most simplest example. Assume you have two participants, then these are the two different decompositions you have. Then you take the first one. Here you have your first complete conditional. This you would like to keep. This is your incomplete. You would like to get rid of that. So you replace this one by marginalizing over the second decomposition here, what you can see here. This is the green one. So what you have is now you have a equation with your unknown, with the first incomplete, perfect, with the second one. And what's remaining is like the second incomplete. You also want to get rid of this one. So what you do, you replace this by marginalization over your unknown, your joint. And now you have a very nice equation system, which is only dependent on your unknowns here. These are the different probability values of your joint, and these incompletes. So for this special case of two participants, you get a linear equation system, yeah? Very easy to solve. And this equation system has certain properties which makes it even easier to solve it. If you extend this to more than two traffic participants, then you get nonlinear polynomial equations. This you can also solve with a polynomial solver, for example, but there are even other ways to solve this correctly, which I will not show here. I will now go over to an example. So we evaluated this on some, as a proof of concept on exactly this kind of maneuver. So we took the NGSIM interstate data set. These are data, like you can see here, videos from above, from these large highways. So here you can pick out quite a lot number of entering scenarios with different configurations. So here we picked out 1070 ones, and here we have from these real tracks you can pick out measurements like relative velocities and positions and what you need, what you assume is needed as a measurement vector, and you can now do predictions within some time horizon of 5 seconds, for example. We assumed here for each of the cars, we took always the car entering here on the driveway, and then we picked out the most 2 nearest neighbors, said, okay, only these interactions count. When we defined 3 different maneuvers for these cars, and so we had like to estimate 27 unknowns. So we did this for 3 different cases. First of all, we did this for this fully interaction respecting case, which I just explained you beforehand. And then we decreased the level of interaction awareness a little bit. We took out only 1 decomposition, neglected the other ones. So the one that is most prominent one for this situation. So we said, okay, we take a complete for the B1 here, who wants to enter. Then we have no interaction for the B2 because he's like in front. Doesn't matter about the one behind. And here, there's only partial fully connection. You have the B3 only includes B2, sorry, and not B1, yeah? Which you usually would take into account. And the final model is assuming simply complete independency. And yeah, some words about the measurement vector we used. We used here the absolute velocities of all these cars, then the relative velocities between these cars projected on this blue line here, and also the difference, the relative distances between the vehicles. Then we learned for each of these conditional probabilities with a logistic regression multi-class classifier, one versus all strategy, these probabilities, yeah. And once we had this, then we had a test sample and tested our inference algorithm. And here you can see the result. So what you can see here is the average receiver operator characteristic for these 3 different kinds of level abstractions, like for the independent case is shown here in blue, for the one decomposition shown here in red, and for all the decompositions, so fully interaction, in green. Receiver operator characteristic shows the false positive rate against the true positive rate here, and the more these curves are in the left upper corner, the better the performance is. So measure is the area under the curve, and as you can see here, that if you take into account all the interactions, it performs best. If you take into account only one decomposition, it's getting worse. And the independent case is the worst one, still quite good. So you can say, if you do exact inference and take all the interactions into account, you are better in estimating like what will happen in the future for this kind of scenario, as an example. Okay, for a summary. So we presented some framework for multiple interacting traffic participants. This can be generalized to an arbitrary number of traffic participants, and we have evaluated on real data. Of course, we would like to do more other traffic scenarios, yeah, but with the same framework. Well, this framework will always be the same, but will now show how important are interactions for other scenarios. Yeah, things to do. Of course, everybody can now use his favorite classifier, try out learning these conditional probabilities. There you can tune the system a lot, or if you put in more data, show how this generalizes. The core part would be here solving the equation system more efficiently, and in a follow-up publication we will show how you can solve this with a recursive procedure of solving linear equation systems. But the most important part for me is, once you have now this fully joined, you can do a rating on the probabilities, which interactions really count. Yeah? If you have a low probability for some interaction, then it seems to be that it isn't necessary to model it. So you could then, in return, use, again, independency assumptions to make your algorithm more efficient again. So as a take-home message, if you want to model, or if you want to use inference efficiently, you first have to model complete dependency. Thank you.
Thank you for excellent timing. Can you have questions, please? We have time only for one question. Any question, please? Yeah, go ahead.
I wonder how you take into account the reaction time of all your participants. That might be different and lead to unstable behavior.
Yeah, it would be a very nice idea to do. We didn't do it so far in these examples, but definitely you have to take more things into account.
Thank you for short answer, that's good. So could you please join me thanking to the speaker?
We move on to the next speaker now. The next speaker is Johannes Bach from FZI. He's going to present a model-based scenario specification method to support development and test of automated driving functions.
Thank you for your introduction. My name is Johannes Bach. I'm going to present the model-based scenario specification method to support development and test of automated driving functions. I'm going to start with a brief motivation and some related work. Then I'm going to present you my concept of driving scenario abstraction. We utilize this concept in a modeling approach and a prototype implementation. I will finish with a short conclusion and outlook on future work. The automotive development process is based on a sequential model reference defined in Automotive SPICE, and this uses the V-model principle. Methods and tools used in the automotive development process support the exchange between different phases, different roles, systems and companies. Many systems and software engineering approaches are utilized to split up big problems into small ones. We have modularization, we utilize hierarchies, and we utilize abstraction to enable to tackle small challenges and reduce the complexity. For example, for large software products, specific languages like the Unified Modeling Language are used. And to further concentrate on concepts that are our development approaches, we utilize, for example, rapid prototype systems in very early phases of development, so we can focus on the most promising approaches for system design. Now with automated driving functions, these standard procedures are tackled, are challenged, and for my work here, it's the main challenge is that with increasing environmental perception and multi-layered algorithms and increasing interactions between components, systems and inter-vehicles, the system boundaries are no longer closed, and this complicates this sequential development process where you start with a specification of what you want to develop and break it down throughout the process, and in the end you're gonna test exactly against your initial specifications. So that's what we're currently doing, and this current verification and validation methods are challenged by this increasing number of software systems in the vehicles. And this is called the 10 × 9 miles challenge, because right now the final release of vehicles is very prominently based on real-world verification drives, and we have to move into further virtual methods. To enable this move into further virtual methods, we lack an approach to specify the vehicular environment, and therefore we need an abstraction concept that keeps a consistent course of events in a traffic scenario, but allows us to specify very early the abstract concepts of what is happening in a traffic scenario, so that will help us in early phases to specify exactly what a assistance system or an automated driving system has to encounter for as a driving scenario, and what it shall behave in this driving scenario. And then it allows us traceability throughout the whole development process, because we have exactly defined what we want to solve. And further on, for test development, it will allow automated generation of testing scenarios with complex driving scenarios that exactly keep up in the consistent course of events, so that we can create many variants of specific traffic scenario. And for real-world testing, it would allow us to analyze recorded tracks and to see where are the relevant scenarios in our real-world test drive, and to derive realistic driving scenarios to use in our virtual environment. So, to describe this complex driving scenarios, there is previous work, and Mr. Geyer provided us with a ontology that utilizes a movie and theater-related terminology for specification of use and test cases for automating driving functions. Here a test case consists of a sequence of several relevant scenarios that are happening along a predefined route that the system under test is taking. A situation is described as the aggregate of all the participants within a traffic scenario and their intentions, and the scenery, the scene of this situation is described by a static scenery like the roads and traffic signs. And this detailed terminology they proposed in their work is a basis we use for further development and to put our abstraction concept on it. This work was picked up by Ulbrich, and he provided more an egocentric view from the viewpoint of a system developer. And there's some distinctions between those two approaches. Ulbrich wanted to specify the distinction between scene and situation more. So what he says, it's a scene is the agglomeration of all participants' self-representation within the static environment, and a situation is only the relative representation of this scene with the intentions of all the participants in this relative representation. So if you look on the right side, here you can see this is a scene, and this is the overall representation of what is happening. And down here, this in red is the situation for the following vehicle. Because this vehicle isn't relative for this, relevant for the following vehicle. And green, this is the relevant situation for the green vehicle. And a scenario is just a succession of many scenes in a temporal way. We utilize a ACC approach and follow maneuver to describe our modeling approach. This is a vehicle that's driving at 100 kilometers per hour, then leading vehicle is entering its field of view and the vehicle is decelerating and then following the lead vehicle at the lead vehicle's velocity with the defined time gap. If we break up this, we have like a sequence of many snapshots. These are all single scenes that happen along the time. We can now use the velocity of the following vehicle to further evaluate this scenario. By velocity here in this case, we can group many snapshots, single scenes together and say, so in the first, all snapshots of the first 13 seconds belong to the free cruise maneuver, the vehicle, the following vehicle performs a free cruise maneuver. So this is all a similar act, we call it. And then in the next act is when the lead vehicle enters the field of perception of the following vehicle. And we have to, the following vehicle has to adjust its velocity to the lead vehicle. And if this process of adjusting the velocity is complete, we have a following maneuver, and all those single snapshots can be grouped together in the following scene. So what do we need to describe such a scenario in an abstract model-based way? So the base of all the description is a scenario that postulates the development of events. It encompasses a static scenery that doesn't change throughout the whole scenario. The temporal abstraction is defined by sequential acts that group the similar scenes. We have we can model participants in the scenario, and these participants, for spatial abstraction, what is also very important if you want to be able to derive different parameterized scenarios that follow the consistent course of events. So we have to abstract also the spatial relations. And we propose to abstract those spatial relations by introducing perception layers in which the interactions and the perceptions of each vehicle is described. And based on those abstraction layers, vehicles are allowed to perform predefined maneuvers. Those maneuvers abstract the intention and actions a vehicle is taking. And from one act to another act, transition is defined by an event. Those events are always defined to specified as a relative relation, for example, against another participant, or for the beginning against the state of at the beginning of an act. So by using always by using always relative values here to define the events, we can always keep this sequential and consistent, this sequential order of events in a consistent way. We implemented this modeling approach in Eclipse meta model as an Eclipse meta model and define the domain model, which allows us to generate scenario instances. What we need to define all those maneuver types is we need a rules and conditions set against which we can check the defined scenario instances. And we have a mapping that allows us to map these entities here against the signals in our recorded test data. And with those rules and conditions, it is enabled that if we parameterize a test run for a vehicular simulation, we can check if this parameterization still keeps up with the consistent course of events that is defined in the scenario. This is the prototype we developed for to check the modeling approach and how feasible it is. We utilized Eclipse and a plugin that's called Perfecti for visualization, and what you can do here now is you can specify a driving scenario and then apply an parameterization and analyze this with the help of the defined rules and conditions. These rules and conditions for maneuver types, for example, we can specify specific situations that have to be present that this maneuver is allowed. Like for free cruise, we define a vehicle that is the ego vehicle that shall perform the free cruise maneuver, and we have this perception layer, so this far field, midfield and near field perception layer. These perception layers aren't yet parameterized, but they are on an abstract level. And here, in all the perception layers, it is it is mandatory that there is no vehicle in this. And so we can do this also for an approach, where we have also to add some information about the vehicle states, and we can do this for the following maneuver. So, what I presented is the related work about scenario abstraction and the terminology used in this field. An abstraction concept that allows us to define driving scenarios, complex driving scenarios on a level that doesn't need to keep up with physical parameters on a physical level, but it's moving all the information onto a logical level, a modeling approach that implements this abstraction concept, and a prototype for evaluation. For future work, we have to evaluate this abstraction approach with much more multi-participants, we have to define and evaluate further maneuvers, but that's really easy with this implementation, because it's all done in the implementation. You don't have to touch the modeling anymore. And currently we are applying it to real-world measurements, and thereby we're always adding further maneuver types to be able to process all the measurements we get from our partners. And in the next step, where we have to change the domain model again, that is the integration of further static scenery elements as reference points. Right now, this does only support highway scenarios, but we have to definitely find a way to include, for example, intersections, traffic signs, and all these types of scenery elements that can happen in real world. So, I thank you for your attention, and if you want to ask any specific questions or give me some recommendations, my post is upstairs in Open Arena, number 18. Thank you.
Thank you. We have just time for maybe one short question. Penny?
Thank you, very nice work. If we connect your work together with the previous presentation from Virginia Tech, so if I want to reconstruct an accident scenario, then I don't need only velocity control, also I want to prescribe the trajectory. Do you have some thinking about that?
Yes, I thought about this. Such accident scenarios, I'm not sure if this is applicable for accident scenarios and this kind of detailed scenarios where you have to keep the exact physical relations, because I'm not sure if this makes sense to abstract these traffic scenarios and probably add different velocities afterwards if you do parameterize it. Probably this is a way that you can ensure that those two vehicles will hit again, and that you can vary many parameters around the accident, but I'm not sure if it makes sense to vary recorded accident database values.
With that, I think we can close this session here. And then thank you all for the presenters again, and thank you for all your participation.